Section 22, Baryogenesis and Big Bang Nucleosynthesis, BBN. This section was updated February 2025. We have looked at the universe from 1 year after the Big Bang to 1 billion years. Now we jump back to 2 seconds after the Big Bang with a little information from the first millisecond as well, and work forward. Protons and neutrons combine to form deuterium and helium nuclei and a small amount of lithium in the first 5 minutes, 300 seconds, after the first 2 seconds after the Big Bang. This is called Big Bang Nucleosynthesis. We could say fine and leave this subject here and move on, but there are several reasons to learn more. To learn the composition and conditions of the universe at this time, because the conditions are different than the cores of stars, because carbon, oxygen, and other nuclei heavier than lithium were not formed at this time, but would be formed in stars later, and because cosmologists' model of the universe must be consistent with the ratio of deuterium and helium to hydrogen when the universe was 5 minutes old, and this ratio can be measured from starlight today. So we will spend some time on this period. Energy density was dominated by radiation, and the scale factor was proportional to the square root of the time since the Big Bang in this period. Going from 2 seconds to 300 seconds, a factor of 150, the scale factor increased by a factor of square root of 150 equals 12.25. Temperature decreased by a factor of 12.25. Radiation energy density decreased by a factor of 150 squared equal 22,500, as did radiation pressure and ordinary matter pressure. Matter density decreased by a factor of 150 to the 3/2 power equal 1837. In this graph, the horizontal axis is time from 0 to 300 seconds after the Big Bang. The scale factor is the blue curve on this graph, with its scale on the right-hand side. The universe is expanding, but decelerating. The blue curve curves downward. 2 seconds after the Big Bang, the scale factor is about 3 by 10 to the minus 10. Here. 3 billion times smaller scale than today. From 2 seconds to 300 seconds, a factor of 150, the scale factor increased by a factor of square root of 150, which is 12.25, which I might sometimes say as 12. Radiation, photons and neutrinos, neutral elementary particles with mass much lower than electrons, had energy density 1,000,000 times the energy density of matter 2 seconds after the Big Bang, and 82,000 times at 5 minutes. So radiation dominated expansion of the universe. Dark energy was utterly insignificant. The radiation energy density and radiation pressure were much higher than at the core of the Sun. I did not put the radiation energy density and radiation pressure on this graph. Background neutrinos played no role in the next few minutes of the universe. Dark matter was 84% of total matter, as it is today, but dark matter played no role in the next few minutes of the universe. 2 seconds after the Big Bang, the density of protons and neutrons was 2% of the density of water now, or about 1/10,000th the density at the core of the Sun, and it decreased by a factor of 1837 over these 5 minutes. So these are not the matter densities where nuclear fusion occurs at the core of a star. The density of ordinary matter is the gold curve on the graph, but the scale for this curve is not shown. Actually, this excludes electrons in the first 10 seconds for a reason we will get to later. Temperature is the red curve on the graph, with its scale on the left-hand side, from 0 to 10 billion Kelvin. 2 seconds after the Big Bang, the temperature was 9.4 billion Kelvin, 600 times higher than the core of the Sun, but not as hot as particle accelerator collisions on Earth. No longer hot enough to create proton-antiproton pairs, nor for protons and neutrons to be relativistic. Temperature decreased by a factor of 12 over these 5 minutes. Two seconds after the Big Bang, the pressure of the kinetic energy of protons and neutrons was about 13 billion atmospheres, about 20 times less than at the core of the Sun, but the radiation pressure was comparable to the core of the Sun. The pressure of ordinary matter fell rapidly. This is the green curve on the graph, with its scale on the left-hand side, from 0 to 10 billion atmospheres. So, 2 seconds after the Big Bang, ordinary matter density and pressure were lower than at the core of the Sun, but temperature was much higher and radiation pressure was comparable, but all values decreased rapidly in the next few minutes. Two seconds after the Big Bang, ordinary baryonic matter consisted of protons and neutrons, with no antiprotons or antineutrons. How did this come about? Let's go back to the first millisecond. Protons and neutrons are baryons consisting of 3 quarks bound and confined with a sea of gluons. This image here shows all the elementary particles, including quarks and gluons. Here's gluons, here's up quark and down quark. The proton consists of up quark, down quark. The neutron consists of up quark, down quark, down quark. You won't need to know that for the rest of the video. Antiprotons and antineutrons are antibaryons consisting of 3 antimatter antiquarks bound and confined with a sea of gluons. Antimatter counts as ordinary matter for expansion of the universe. Antimatter is not antigravity. Pions are mesons consisting of 1 quark and 1 antiquark bound and confined with a sea of gluons. The physics of elementary particles, after 1/1,000,000th of 1 second after the Big Bang, is pretty well understood and verified using our most powerful particle accelerators. The Large Hadron Collider at CERN, whose range of operation is shown as this green bubble, and the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Lab, whose range of operation is shown in this blue bubble. about 100 microseconds after the Big Bang, the temperature fell to the point where the average photon energy fell below 300 million electron volts. The high temperature, high density, liquid-like quark-gluon plasma, shown here, throughout the universe became less dense than a proton's internal energy density. The quarks and gluons underwent a phase change from quark-gluon plasma to now a plasma of individual hadron particles, shown at the lower left. This might be a proton, this might be a neutron. The individual hadron particles, 3 quark baryon particles and antiparticles, such as protons and antiprotons, neutrons and antineutrons, and 2 quark mesons, such as pions, not shown here. This phase change is a kind of freeze-out, though very hot. One description goes that the continuous liquid ocean of gluons froze into isolated particles of gluon ice and quarks. Except the gluons travel at the speed of light inside the isolated particles, so not exactly like ice. The red, green, and blue colors in this image represent color charge, not quark flavor. And the color charge is not important to this course. I think we should also see equal amounts of anticolors, cyan, magenta, and yellow, in the quark-gluon plasma, but it doesn't affect our course. The temperature was now low enough that proton-antiproton pairs, neutron-antineutron pairs, and pion-antipion pairs annihilate and are not recreated. Quarks and antiquarks are believed to have been continuously created in pairs, equal numbers, since the early universe, continuously annihilating in pairs and being recreated in pairs. At 1 microsecond after the Big Bang, their number and energies would have been comparable to the number and energies of photons. When temperature falls low enough in the first millisecond, the simple case would be that all the quarks and antiquarks would annihilate in pairs, equal numbers, leaving 0 quarks and antiquarks, 0 protons, 0 neutrons in the universe for the remaining lifetime of the universe. No hydrogen, no stars, no Earth. However, somehow, shortly, there would be a small residue of protons and neutrons, and no more antiprotons and antineutrons. Somehow, 1 out of a billion antiprotons did not annihilate with a proton, but perhaps decayed to leptons, electrons, or muons. This violated conservation of baryon number, but kept the universe electrically charged neutral. This left some protons to survive, with an equal number of electrons. This process is called baryogenesis. Physicists know the 3 conditions required to cause this, some of which have been observed in particle collider experiments, but they do not know the specific mechanism and process at work in the first millisecond of the universe. So we no longer need to be concerned about antiprotons and antineutrons. We no longer need to talk about quarks. We could talk about the surviving protons and neutrons. This formula shows reactions that can go from the left to the right or the right to the left. N is neutron, P is proton, E minus is electron, E plus is positron. This nu is an electron neutrino, and this is an electron antineutrino. Neutrinos are electrically neutral elementary particles with much smaller mass than electrons. Immediately after baryogenesis, 1 millisecond after the Big Bang, protons and neutrons could turn into one another pretty freely. They were in thermal equilibrium with electrons, positrons, neutrinos, and photons. The neutron has slightly more mass than the proton, so neutrons were fewer than protons. Numbers on the left side of the equation were lower than the numbers on the right side. The ratio of neutrons to protons shown in this graph decreased as temperature fell, as shown in this graph. In this graph, the horizontal axis goes from high temperature on the left to low temperature on the right. Before 1 second, neutrino-antineutrino pairs had also stopped being created. Neutrinos decoupled from matter, from protons, neutrons, and electrons, and perhaps also from dark matter. Neutrino-antineutrino pairs could no longer annihilate to produce electron-positron pairs because their relativistic energy fell below the electron rest mass. These primordial cosmic neutrinos played no further role for most of the life of the universe. These cosmic neutrinos and antineutrinos have been traveling the expanding universe since the first second, losing energy due to cosmological redshift. Neutrino rest mass energy is much smaller than an electron, so neutrinos were relativistic and count as radiation for most of the age of the universe. Cosmologists would like to detect these relic cosmic neutrinos to shore up the model for the first second after the Big Bang. These cosmic neutrinos are passing through your body every second of your life. For the remainder of this video, we no longer need to be concerned about neutrinos. 1 second after the Big Bang, free protons are no longer converted to neutrons because neutrinos have decoupled, and the ratio of neutrons to protons froze out here at 1 neutron to 5 protons, a ratio of 0.2. There were 1.6 billion photons for every proton or neutron. Two seconds after the Big Bang, the average photon energy was 2.2 million electron volts, gamma rays, which could still create electron-positron pairs. For every proton or neutron, there were about 1 billion electrons and antimatter positrons. They were relativistic and counted as radiation, not matter for driving expansion. Around 10 seconds, temperature had fallen to the point where electron-positron pairs ceased to be produced, and they annihilated, producing gamma rays. Though electrons and positrons were believed to have been created initially in equal numbers and should have annihilated in equal numbers, leaving 0 electrons in the universe, Somehow there was a small residue of negatively charged electrons, exactly balancing the positive charge of the residue of protons, so the universe as a whole was electrically neutral. This is called leptogenesis. I'm not a physicist, but to me, it seems like some of the antiprotons probably decayed into electrons, resulting in the residue, but keeping electrical neutrality. Soon thereafter, the electrons were non-relativistic and counted as matter, not radiation. Electrons and positrons played no role in Big Bang nucleosynthesis, though there is this overlap of the timeline. So we won't be concerned about electrons or positrons or neutrinos for the rest of this video. Big Bang nucleosynthesis. Protons and neutrons start to fuse, nuclear fusion, 2 seconds after the Big Bang. This is called Big Bang nucleosynthesis. This graph shows one particular model's prediction of the mass fractions, fraction of ordinary matter mass, of the protons, neutrons, and other nuclei for the first 50,000 seconds, 14 hours, after the first 2 seconds after the Big Bang. The horizontal time scale and vertical mass fraction scale are logarithmic. Temperature, pressure, and total ordinary matter density are falling rapidly with time. Most of the activity is complete by 300 seconds, the green vertical line. Initially, there was 1 neutron to 5 protons, or 10 protons to 2 neutrons. The mass fractions were 0.83 for protons and 0.17 for neutrons, shown at the upper left of this graph. The top solid line, here to here, is protons, ordinary hydrogen. The short dashed line below it at the upper left is free neutrons. Here to there. The medium-sized dashed line below the solid line at the upper right is helium-4. 2 protons, 2 neutrons. Here to there. If all the neutrons had been completely incorporated into helium-4, we would have ended up with 1 helium-4 nucleus for every 8 free protons. The final mass fractions would be 8 out of 12 equals 0.67 for protons, and 4 out of 12 equals 0.33 for helium-4. This is close to what happens, but the actual final mass fractions, shown at the upper right of the graph, were 0.76 and 0.24, with 1 helium-4 nucleus for every 12.7 free protons. Since the helium-4 contains 2 protons and 2 neutrons, the right-hand side has more total protons and fewer total neutrons than the left-hand side. This is because each free neutron decays to a proton, an electron, and an electron antineutrino with a half-life of 10 minutes. So some of the free neutrons turn into protons during this 5-minute period of Big Bang nucleosynthesis. 23% of the neutrons decay into protons in the first 230 seconds, before much helium or deuterium has been created. So, the mass fractions of protons and neutrons become 0.87 and 0.13 at 230 seconds. About here. The top solid curve is for protons. Protons start out with mass fraction of 0.83 on the left, red number, rise to 0.87 at 230 seconds because some of the neutrons have decayed to protons, and finish at 0.76 on the right. Protons are stable particles, and these protons would later be hydrogen atoms and ions throughout the universe, in cosmic voids, intergalactic medium, interstellar gas, in stars, and on Earth. The second small dashed curve on the left-hand side is for neutrons. Neutrons start out with mass fraction 0.17 on the left, purple number, fall to 0.13 at 230 seconds due to decaying into protons, and then fall precipitously with fusion, as we will see next. After 300 seconds, the remaining free neutrons decay to protons in this decay curve. A neutron is electrically neutral and readily binds with a proton via the strong nuclear force to form deuterium, hydrogen 2, 1 proton and 1 neutron. The binding energy of deuterium is 2.22 million electron volts, loosely bound for a nucleus. This fusion step to form deuterium does not require the high temperatures of the cores of stars because there is no Coulomb repulsion between a proton and a neutron. The neutron is electrically neutral. Actually, it requires that the temperature be less than about 780 million Kelvin for the many high-energy photons to not dissociate the deuterium back to a proton and a neutron. The formation of deuterium, the solid line in the middle of the graph, so going from here to here, and then ending up here. The formation of deuterium was able to proceed at increasing speed from 2 seconds to 300 seconds. As the temperature decreased from 9.4 billion Kelvin to 770 million Kelvin. Had there been no other fusion reactions, the final mass fraction of deuterium would have been 0.24. But there were other reactions. At these temperatures, a deuterium nucleus can fuse with a proton, overcoming electrical repulsion, to produce a helium-3 nucleus, which can then fuse with a neutron to produce a helium-4 nucleus. This is the most probable reaction because so many protons are available. But this only works for a short period before the temperature drops too low to overcome repulsion. This is the helium-3 curve. Or a deuterium nucleus can fuse with a neutron to produce a hydrogen 3 nucleus, which can then fuse with a proton to produce a helium 4 nucleus. This is the curve for hydrogen 3, tritium. Two deuterium nuclei cannot fuse to produce a helium 4 nucleus in a single step because they need a way to shed binding energy as kinetic energy. But there are two-step processes. So, helium 4 takes up most of the neutrons within 300 seconds, and its mass fraction ends up at 0.24, as seen in the outer layers of most stars. Helium is 23.8% by mass of our Sun's outer layer. Helium that our Sun produces by fusion in its core does not get convected to its surface. Deuterium here, helium 3 here, and hydrogen 3 here are lesser end products of Big Bang nucleosynthesis. Deuterium and helium 3 are stable and exist in the universe today, but the hydrogen 3 decays to helium 3 with a half-life of about 12 years. So all of that initial hydrogen 3, tritium, was gone long ago. Helium 4 does not fuse with single protons or neutrons. However, to a small degree, it will fuse with a deuterium or hydrogen 3 nucleus to produce lithium 6, which is this curve, or lithium 7, which is this curve. And those are stable. So those survived until today. Helium 4 and helium 3 can fuse to produce beryllium 7, which is this curve. Beryllium 7 decays to lithium 7 with half-life of 53 days. So the lithium 7 concentration today is an order of magnitude higher because beryllium 7 got produced and it decayed to lithium 7. Two helium 4 nuclei can fuse to produce beryllium 8, but it decays back to helium in less than a trillionth of a second. Because of this beryllium bottleneck, Big Bang nucleosynthesis produces no carbon or oxygen nuclei at all, and it is largely complete by 500 seconds. The beryllium bottleneck will later be overcome in stellar cores that fuse helium to carbon at high temperature, pressure, and density, with the luxury of time and density that Big Bang nucleosynthesis does not have because of the expansion of the universe. Deuterium is 150 parts per million of hydrogen in water on Earth. Nearly all the deuterium on Earth came from the Big Bang nucleosynthesis, but none of our helium did. It came from alpha decay of uranium and thorium. That's because when Earth was formed and was hot, it wasn't massive enough to have enough gravity to hold the primordial helium. So that helium is escaped. It did not escape the Sun's gravity or Jupiter or Saturn's gravity, but it did escape Earth's gravity. Some of the lithium on Earth came from Big Bang nucleosynthesis, but most came from dying low-mass stars ejecting mass before our solar system was created. It turns out that the solid form of molecules of lithium with deuterium is the fuel in thermonuclear bombs, lithium deuteride. And deuterium is part of the fuel for fusion reactors. Hydrogen-3, tritium, is also a fuel in thermonuclear weapons, and its half-life is about 12 years. So that half-life is a factor in maintaining the nuclear stockpile. Weapons that are, 30 or 40 years old have to be modeled to see whether they still contain enough tritium to create the desired explosion. Now, the tritium in those weapons is man-made on Earth. It's not from the original Big Bang nucleosynthesis. Most of the stars in the Milky Way are less massive and less luminous than the Sun and are called brown dwarf stars. These stars fuse primordial deuterium with protons in their cores, but are not hot and dense enough to fuse protons together. These stars will continue to fuse deuterium for hundreds of billions of years. It turns out that the predictions of Big Bang nucleosynthesis and the temperature and time of hydrogen plasma recombination that results in the cosmic microwave background are connected, and that both processes depend on the number of photons per baryon in the universe, 1.6 billion, because both processes depend on high-energy photons. And so astronomical measurements today can quantify the photon-to-baryon ratio that has been constant since the first second after the Big Bang. The ratio of deuterium to hydrogen-1 after Big Bang nucleosynthesis is said to be around 25 parts per million. Astronomers check the Big Bang nucleosynthesis predictions by using spectrometry to measure the present deuterium mass fraction in the interstellar gas in our neighborhood of the Milky Way and the deuterium to hydrogen ratio in intergalactic gas, including absorption of light from quasars, and the helium mass fraction of the outer layers of stars similar to the Sun. Astronomers have not found as much lithium as predicted by Big Bang nucleosynthesis. This is called the cosmological lithium problem. Here is the history of our universe in 15 seconds that we've seen before. First there was nothing, then there was something. We have not yet learned about this. Then there was hydrogen. We learned about that today. Then there was dirty hydrogen. We learned about that today. Dirty hydrogen is the primordial mix of hydrogen, helium, and lithium after Big Bang nucleosynthesis. First, the dirty hydrogen was ionized. Then it was neutral at recombination, photon decoupling, and last scattering. Then it was ionized again at reionization by the ultraviolet light from stars in early galaxies. So we have now seen how hydrogen and dirty hydrogen were created. We have now completed the timeline of the universe from basically a few trillionths of a second after the Big Bang to 1 billion years after the Big Bang. Next, we cover the first billionth of a trillionth of a trillionth of a second, 10 to the minus 33 seconds.